up and running and live and all that good sort of stuff. How is everyone today?
It's a blah day.
It's a blah day, unless you're a worm or a bird, in which case it's a really exciting day. Well, so we've got less than 50% of the students here. We had like 50% in 222 earlier. So I guess people are taking the attendance thing to heart. All right, so anyway, welcome to the people who are here. Any questions from last time? We were talking about sets and set theory.
Yeah, I actually have a question on the homework.
Cool.
If possible.
Sure thing.
So you would be willing to try to pull up my work.
Yeah, I'm pulling it up here too.
Alright. Specifically, like, when we're talking like the brackets, and the first one, number 2a, is like 1 over n with a line, and n is a member of the set of numbers. When it's saying list all elements of the following sets, is it talking, that line specifically, is it saying that 1 over n is a part of that element, or is it wanting us to list just the numbers within the brackets, or?
So I don't remember what the exact problem is, but something like this, right? Set of 1 over n such that n is contained in some set, right?
Yes.
So the elements of this set are elements of this form, where n could be a 2, a 3, or 4, or a 5. So the elements of this set would be exactly 1/2, 1/3, 1/4, and 1/5.
Okay. Because the way I was reading it, because that little weird E symbol, it says is a member of that brackets. To me, that doesn't state that it is actually those set of numbers.
Mm-hmm. Right, it's any number that's in that set. So for example, n could be a 2, because that's a member of this.
Okay.
And so 1 over 2 would be a member of this whole set.
So that specific symbol means a little different than what I originally thought it was.
Okay. So yeah, this is a pretty typical way to do set notation. The set of all x plus 1 such that x is bigger than 10. So the elements of this set would be, assuming we're talking about integers here, any x that's bigger than 10, well, for example, 11, so 11 plus 1, 12 would be a member of this set. If x is 12, that's bigger than 10, and so 12 plus 1, which is 13, would be a member of this set, and so on.
That makes sense.
Right, so it's the set of all these things such that that thing.
Okay. Yeah. Going over the material and having done the last meeting, I was like, I think I have a handle on this, and now I'm like rethinking everything. Okay.
Okay, yeah, I think you got a handle on it. So let's go over the homework assignment since we're here anyway. So 1.1 questions 2 and 4, 1.24, and so on. So let's start with 1.1, questions 2 and 4. So 1.1 question 2, list all the elements of the set. Hey, I almost got the set right. That was from memory. List all the elements alpha contained in the alphabet such that alpha precedes F. Precedes means comes before F. And so on and so forth. Here P is the set of positive integers. Here P is the set of positive integers. So you're listing the elements of those sets. And then question 4, use set builder notation to describe the following sets. So remember, set builder notation is when you do something like this, the set of all something such that something else. And so here you're looking for patterns, right? I mean, we could say the set of all x such that x is contained in this set, but that's not really using set builder notation. But, you know, we could say, for example, a set of all x such that x is bigger than or equal to 1 and less than 8 and contained in the integers. So look at these and think about patterns and try to find a way to describe that. Try to be creative on D. Don't just say the set of all x such that x equals 0, because you're using this in your definition of the set, and that's kind of circular. But try to find a different way using set builder notation to represent the set containing just 0. A lot of these...
Does this mean that set building notation could be written differently depending on just perspective?
Well, it's generally going to be, you know, the set of something such that something else. But the particulars of this can be very different, and there may be multiple ways to write something in this notation that would represent the same set. For example, I could have written this as, you know, the set of all 1 over n such that n is bigger than or equal to 2 and n is less than or equal to 5. Or the set of all 1 over n such that 1 over n is bigger than or equal to 1/5 and 1 over n is less than or equal to 1/2. And those would all, you know, reduce to the same set containing those elements. So yeah, there's definitely multiple ways to do these. All right, and then 1.2, question 4. So we're going to talk about set operations next. And so we're going to talk about these intersections and unions and subtractions and so on and so forth. So 1.2, question 4, give examples to illustrate the following facts. So for example, if the universe that we're working with is just the integers from 1 to 9, and that's the universe for all 4 of these parts, right? So any sets you use for question 4, the elements have got to come from this set 1 through 9. So we're asked to show an example of sets A, B, and C where this and this are true and this is also true. So my clarifying note here was, give an example means show or describe exactly the contents of the sets. Show or describe exactly the contents of the sets on both sides of the equal sign, showing all of your work, and then state clearly whether the two sets are equal or not. So for example, in B, we're going to talk about what subtraction means. We're asked to show that A minus B is not always equal to B minus A. You want to pick a particular set A from this universe and another set B from this universe. You want to write down, let A be the set blah, let B be the set blah. And then write down A minus B equals and show me what that is. And then write down B minus A equals and show me what that is. And then simply make the observation that those two are not the same. And so that's an example where A minus B is not equal to B minus A.
Now, real quick, just to double check. It's very much saying that U is this specific set of numbers, but we're not being given a set of numbers for A or B or C.
Exactly.
So we're just giving them numbers?
Yeah, you're just deciding for yourself what you want the sets A, B, and C to look like.
Okay.
And you can pick an A, B, C here. You might pick a different A, B, C, or A, B here. You might pick a different A, B over here and a different A, B, C here. But the universe is always just the set 1 through 9. So we're not proving these things, right? We could do a very formal mathematical proof and show that if A is a subset of B and B is a subset of C, then A is a subset of C. We can prove that, but that's a much harder thing to do. All you're asked to do here is give examples to illustrate these facts. So what's an example? Well, you pick a set A, you pick a set B, you pick a set C, and you say, hey, you know, A is a subset of B, B is a subset of C, and guess what? A is also a subset of C. Right, so later on we'll get into proofs and we'll actually rigorously show that these things are true. But usually when you want to prove something, you start off by working some examples, right? And you do that to kind of get familiar with the problem and to start to see, you know, in your own mind some things that are sort of forcing this thing to be true. And if you do enough examples, you'll start to see patterns. You'll say, hey, you know, every time that I do this, this thing happens, and then when I do that, this other thing happens, and those two things will always make this third thing happen. And it doesn't feel like it matters what those first two things are, because they're always going to make that third thing happen. And then you start seeing a pathway to writing up a proof. So this is sort of a initial step to what could be the process of doing a proof, but it's not that formal. All right, and then 1.2, number 6. Think about number 8 and make a try. So number 6 is talking about infinite sets, which we're also going to talk about today. Number 8, I want you to just sort of think about this and play around with it. It's a fun sort of problem. And later on, when we talk about counting, we'll see some pretty powerful machinery for attacking this in a very formal way. But just play around with it up front and think about it. It's a good way to get a little deeper into some of the concepts of sets and complements of sets and the size of sets. So think about this one.
For 8, let u equal, or I don't know, absolute value. What's the double line called again?
The cardinality?
Absolute value.
Yeah, it's the cardinality. For us, it's just the size of the set.
Okay, so let the size of u equal, is that 16 comma 3 zeros comma, or like...
That's 16,000.
16,000?
Yeah, this is 9,000.
Okay, it's just kind of a weird space.
Yeah.
Okay.
Yeah, I think the typesetting for this book always put a space after a comma and didn't bother to notice that it's a number.
Okay. What's the upside down u? Or like the upside down union?
So the upside down union is the intersection. We're going to talk about that today, like this thing.
Okay, so we
Yeah.
haven't gone over that.
No, we'll get to that shortly.
Yeah, I was like 6 minutes late, so I was like...
Okay, no problem.
We done already.
All right, and then 1.3, take a shot at number 2. So 1.3 is using Cartesian products, which we talked about on Monday. And so it's just, defining two sets A and B, and then asking you to look at their Cartesian products, see how many things are in there, think about sort of physical interpretation of what the Cartesian product of A and B in this case might be. So that's the thought exercise. So the deal with homework is I'll generally pick one homework problem and grade that. And I won't tell you which problem ahead of time, otherwise, you might only do that problem. So you want to do all these problems. I won't be grading number 8. Okay, that's the one that says, make a try at it. So I want you to think about that and dig into it on your own. But don't worry that, I couldn't figure it out. What if he grades that one? I'll get a 0. I won't grade that one, okay? But we'll talk about it in class. All right, other questions? Well, we got 13 people in here, so we're just over the 50% line now, so that's bonus.
Kind of wish you made attendance required again.
I know, yeah. Well,
it would be in person, but
I'm not gonna record attendance in person either. I might note it down, like I say, for contact tracing and such, but I'm not gonna start factoring it into grades. But hopefully people are gonna be able to make it. So yeah, on the subject of in person, let's talk about week 2. So I'm going to make a decision tomorrow, and I will post it on Canvas to let you know definitively whether week 2 is going to be back to in person or we're going to continue remotely. My sense right now with where numbers are and what I'm hearing from students about contacts and infections and positive test results, my inclination is we're going to keep week 2 remote until the numbers improve. But I'll make a final decision tomorrow, and I'll post something on Canvas in the announcements. Make sure your Canvas is set up to send you email immediately when there's an update, like an announcement. and make sure your email is one that you have access to or is forwarded to your real email. And I'll post a Canvas announcement tomorrow. And hopefully we will get back in person sooner or later. All right, other questions? All right, let's talk about set operations. So my goal today is to talk about set operations, set identities, ways of working with sets, something called membership tables, whole bunch of kind of mechanics of set theory. And then I want to talk about cardinality for infinite sets. So cardinality, those two vertical bars tell us how many things are in a finite set. But if you have a set with an infinite number of things, what do we mean by its size? So we'll talk about that towards the end of class and see where that leads us. We'll also talk about a paradox called Russell's paradox, just for fun. All right, but let's start with set operations. So a lot of what we do in academic subjects, in math, in science, a lot of what we do is we try to make new things from old things. And that's going to be a lot of what we do in this course. So for example, we're talking about set theory. We know what a set is. It's a collection of things. We know how to, talk about the size. We know about subsets and members and so on. So one thing we can do for a lot of fun is we can build new sets out of old sets. And so set operations are different ways we can do that. So let's talk about some set operations. The first one is the union. And if A and B are sets, and I'm just going to assume A, B, C, X, Y, Z, these are just sets we're going to use. So if A and B are sets, we can describe A union B, and it's this little U without any adornments on it. It's sometimes called a cup. So A union B equals the set of all elements such that this element is in A or this element is in B. So A is a set of things, B is a set of things. Take all those things and put them together, that's the union. And so for example, let A be the set containing 1, 2, 3. Let B be the set containing Q, R, and S. So A union B is a set containing 1, 2, 3, Q, R, and S. Nothing too shocking there, right? So the one thing you might need to be careful of, suppose C is the set 1, 4, 6, and A is still the set 1, 2, 3. A union C could be this set. It only contains 5 things. It does not contain 6 things. Right? There's a 1 in A, so there's a 1 in the union. There's a 1 in C, so there's a 1 in the union. But 1 does not magically appear twice in the union. Right? A set is simply a notion of what are the elements of this collection. And in this case, the elements are 1, 2, 3, 4, and 6. So let me say not. Alright, don't listen to element twice. Alright, so another operation we can do is an intersection. So A intersect B equals the set of all elements X such that X is in A and X is in B. So it's the things that are in both. So for example, A intersect B is the empty set, because there's no X anywhere that's in this set and also in that set. What about A intersect C?
One.
That's just the singleton set containing 1, because there's a 1 in A and a 1 in C, but 2 and 3 aren't in C, and 4 and 6 aren't in A. Alright, so we got unions, we got intersections. And there's a piece of terminology here. If two sets have an empty intersection, if their intersection is the empty set, A and B are said to be disjoint. So disjoint sets are sets that have an empty intersection.
Quick question on that.
Yeah.
When you're saying an empty intersection, does that mean that they just don't have an intersection at all?
It means the intersection is the empty set, which basically means there's no overlap between them.
Okay, so does that mean that if you are comparing two lists, that if they do not have an intersection, they would always have an intersection being the empty set?
If they don't have any overlap, then the intersection would be the empty set, yeah. It's a little imprecise to say they don't have an intersection, because we can always take the intersection of two sets, but sometimes it gives us an empty set. It has no elements in it.
Okay.
So yeah, let's say if they don't overlap, if there's nothing in common between them, then their intersection is the empty set, and then we call them disjoint.
Cool. Thank you.
Yeah, you're welcome. It's potentially interesting to note that, the number of things in A is 3, the number of things in B is 3, the number of things in their union is 6, which happens to be 3 plus 3. But here, the number of things in C is 3, but the number of things in the intersection of A with C is 5, which is actually less than 3 plus 3. And so imagine you have two sets, A and B, and A has this much stuff, and B has this much stuff, and you're going to glom them together. At the most, you're going to end up with this much stuff. All the stuff from A and all the stuff from B. But a lot of times, because there might be some overlap, the total amount of stuff you end up with is going to be smaller than this stuff plus this stuff. And so we can actually state a theorem and that's the mathematical way of holding your hands up and using words like stuff. The number of things in A union B is going to be less than or equal to the number of things in A plus the number of things in B. In fact, it will be exactly equal if there's nothing in common between A and B. But it could be less, and in fact it's less by the amount of stuff in common. And so we can actually say something stronger. The number of things in A union B is exactly equal to the number of things in A plus the number of things in B minus the number of things that are in common. So that's a useful fact to keep in the back of your minds, and we'll come back to this in a few weeks when we talk about counting. And this will help us with that question 8 from the homework. But don't get too bogged down on the set theoretic mechanics of it. Think about question 8 just kind of from a common sense point of view. And you'll end up developing this kind of intuition yourself. But then we'll formalize it later on. All right, more set operations. So we have different ways of describing this. Sometimes we'll talk about A minus B. Sometimes we'll write A dash B to mean A minus B. Sometimes we'll write A backslash B. It's got to be a backslash, not like a regular divide symbol, but a backslash. Formally, we'll call this the complement of B in A. And all of these things mean the following: the set of all x such that x is contained in A and x is not contained in B. So A minus B is all the stuff in A after you throw away the stuff that's in B. All right, so example. Let A be the set 1, 3, 5, 7, 9. Let B be the set 2, 3, 4, 5, 6. So A take away B, the complement of B in A, equals basically the set A, where you throw away anything that's also in B. So for example, the 3 gets tossed out, and the 5 gets tossed out. So A minus B would just be 1, 7, 9. On the other hand, B take away A would be start with the set B and throw away anything that you find in A. So for example, the 3 is in A and the 5 is in A. So this is the set 2, 4, 6. All right, everybody clear on this operation?
Makes sense to me.
I usually won't say. I'll usually stick with the complement of B and A, but all these different things are equivalent.
Other paper, please.
Does that make that property commutative?
It's definitely not commutative because A take away B is this, B take away is that. Those aren't the same result. So this is a funny operation. It's definitely not commutative.
Thank you.
Whereas union and intersection will be commutative.
Oh, I see. Okay.
So if U is the whole universe, if U is the set of everything that we could be working with, the collection of all things from which we might build sets, then U take away B, we just write as B with a bar on top, or sometimes B with a little c on top, and we just call that the complement of B. So A take away B is the complement of B in A. But if A is the whole universe, the complement of B in the whole universe, we just call that the complement. And we can write it as a B with a bar on top. Or in the book, sometimes B with a superscripted C after.
I have a quick question.
Okay.
This minus and this backslash, are they the same thing?
They are exactly the same thing.
Okay, thank you.
Yep, just different notations. And this are exactly the same thing.
Why did they create it that way? It doesn't make sense. Why just not use one symbol? It seems very inconsistent.
Well, yeah, there's a lot of inconsistency out there. So this is a typesetting thing, right? When mathematics was being done by hand, this was a very easy thing to do. When people started using typewriters, this became a very hard symbol to create. You'd have to either manually add a dash on top, or you'd have to go back and roll the paper down and type some underscores and things like that. This is a little easier to do, right? You type a B and you just roll the roller half a turn and hit a C and you got a subscript. And so the textbook, for example, uses this notation more than that. Why there's a backslash and a minus, I don't know the origins of that, except backslashes are kind of funny characters. I'm not even sure they're standard on a regular typewriter, whereas the minus sign is. A lot of what you'll find in this course and in these subjects in general is a fair amount of ambiguity or duplicate notions in different forms. These subjects are, hundreds of years old, and that's a long time to try to stick to something consistent. Fortunately, union and intersection, pretty consistent. All right, so we have some set operations, and this is where it may be useful to think about a Venn diagram. So here's our universe. Here's A. Here's B. So this spot where they overlap, that's their intersection. This stuff that we get by looking at everything, whether it's in A or in B or in both A and B, that's the union. If we start with A and we throw away the things that are in B, we get something like this. This would be A, take away B. And if we start with the whole universe and we throw away a set, for example, the whole universe take away B, we would get all of this stuff. Everything except B. That's the complement of B. That's the monochrome version if you're having trouble seeing the yellow. So Venn diagrams are a useful way to think about and understand and explore some of these set operations. Again, we can't prove things with this, but for example, we can get the idea that, the number of things in A intersect B is probably no bigger than the number of things in A. In fact, it's got to be less than or equal to, because we're starting with A and we're throwing away things. The intersection is a little piece of A. But we also get the idea that the intersection is always a subset of A. Well, that turns out to be true, because to be in the intersection, it's got to be in A and in B. So everything that's in here is a subset of A and also a subset of B. So sometimes you can get some useful insights like that. We have
What is the yellow B?
that's B bar, so that's the complement of B. And that's basically everything in the universe that's not in B. So B bar means the whole universe, take away B. All right. Well, we've got some set operations now. Let's look at some of the properties of these operations. So we can talk about set identities. And so again, we'll let A, B, C, all these things just be arbitrary sets. And U is the universe, and we've got the empty set. And so we can start listing some of the properties of these operations. For example, A union A is just equal to A. A intersect A is also equal to A. And you know, the intersection is a set of things that are in this set and in that set. Well, this means a set of things that are in A and also in A. Well, that's just the things in A. If we take A and we union the empty set, we get A. This is a set of things that are in A or in the empty set. Well, there's nothing in the empty set. So this is just the set of things in A. If we take A and we intersect with the empty set, what do you think we get?
Nothing.
We get nothing. Because the intersection is a set of things in A and also in the empty set. Well, there's nothing in that empty set. So anything that we think of, even if it happens to be in A, it's not going to be in here, so it's not going to be in the intersection. So the intersection can't have anything in it. Now if we take A and we union it with the entire universe, what do we end up with?
The universe?
The entire universe. And if we take A and we intersect it with the universe,
A.
you just get A back. Because this is the set of things that are in A and also in the universe. Well, if we pick something in A, we know it's in the universe. So that's going to be in the intersection. And if we pick something that's not in A, it can't be in the intersection because it's not in A. So this is going to be exactly A. If we take the complement of A and we take the complement of that complement, any guess what we come up with?
You're allowed to complement a complement?
Mm-hmm.
Complement anything, right?
Yeah, you can complement any set, and the complement of A is a set, so we can take the complement of that.
Which is just A.
So if this is A, then all of this is the complement. And so the complement of that orange-brown set is a set of things that aren't in the orange-brown set. Well, that's just the stuff in the middle. That's just A. Or if you like, this is a set of things that are not in A. This is the set of things that are not in the set of things that are not in A. Well, if you work through the double negatives, you'll find out that's another way of saying the set of things that are in A, that turns out to be equal to A.
It's kind of interesting that you can use it kind of in the same concept as math. 2 lines equal it's basically a positive.
Yeah, yeah. That's not a coincidence, actually. That's a key insight to what's actually going on. Does this look familiar to anything that we've done in the past?
It does, but I can't put my finger on it.
Yeah.
It feels like, what was it,
Just
250?
Boolean algebra.
Yeah, Boolean algebra, engineering 250. We had rules like this using ors and ands. We had a rule that, A or A is equal to A. A or 0 is equal to A. A ANDed with 0 is a 0. A ORed with 1 was equal to 1. A ANDed with 1 was equal to A. And if we go back and we look at the definition of union and intersection, the definitions are exactly the same, except for the union, we've got an or here, and for an intersection, we've got an and here. And that's also not a coincidence. So unions act very much like ors, and intersections act very much like ands. And in that sense, the empty set acts like a 0, and the universe acts like a 1 in Boolean logic. And so not A was the same as A. Well, that's what this looks like. And in fact, the bar on top of a set looks exactly like the way we write negations in Boolean algebra. So we can continue writing identities, things that are always true about sets, and this is going to start to look even more familiar. So for example, A union B equals B union A, and A intersect B equals B intersect A. That's a property called commutivity. And we can say that ors commute, we can say that unions commute, intersections commute. We can distribute A union B intersect C is the same as A union B intersected with A union C. So if we thought of this as plus and this as times, this is distribution from algebra. And similarly, A intersect B union C equals A intersect B union A intersect C. Alright, here's a showstopper. Anyone remember this?
Morgan's theory.
That's De Morgan's theory.
Use it all the time at work. Great.
Cool. De Morgan's theorem, and there's two versions of it. It says the complement of the union is the intersection of the complements. And the complement of the intersection is the union of the complements. So if we want to split this bar up into individual things, we can do that as long as we switch between union and intersection. And there's a version of that from Boolean algebra. It looks almost exactly the same, except this is an or, this is an and. And we can put a few more up here. A union A bar. So what do you get if you take A and you union it with its complement?
You get everything.
You get everything. Take A and then toss in all the stuff that's outside of A. That gives you the whole universe. And A intersect its complement.
Not me.
Yeah, so this is the stuff that's in A and also not in A. And there's no such element that's in A and also not in A. So the intersection is the empty set. And this is A or A bar equals 1, A and A bar equals 0. So all the stuff we learn in 250 related to Boolean operations has pretty much some sort of parallel in set theory.
Can I see the lower page for a sec?
The which?
The lower page. Lower page.
That one or that one?
No, just the last one. Just the bottom page.
That?
The bottom part. No. It was a list of.
This one?
Yeah.
Okay.
Just the bottom part.
Is it clipped off?
Okay, I see it now.
Okay. Oh, do you have a zoom toolbar at the bottom of your screen?
We do, yeah.
Okay. You should be able to move that. I don't remember how exactly. On mine, I can grab it with an Alt and a mouse click, but that's under Unix, I think.
Oh, I got it down.
Oh, you can just press Alt and it hides them.
Oh, okay, cool. All right, here's one more good identity that may come in useful. A union A intersect B is exactly the same thing as A. And A intersect A union B is also the same thing as A. And this is a property called absorption. And that can be useful sometimes.
I'm sorry, I missed like the first 30 minutes. I know what union is, intersection. Can you just go over that again, please?
Yeah, so AUB, A union B, is a set of all things that are in A or in B. So that's the union. The intersection, the upside down U, is a set of things that are in A and also in B.
Okay, so it's just or and and.
Yeah, so it's just or and and. This is the collection of all things glommed together. This is the things that are contained in both.
Yeah, I've seen that symbol before when I was in algebra, but our teacher never really told us what it was, the union symbol. We used it for defining domains.
Oh, interesting. Okay. Huh, okay. So here's an absorption formula. A union A intersect B is the same as A. And A intersect A union B is the same as A. And there's parallels in Boolean logic to these. But what if we wanted to know, if this was actually true? How could we prove that? How can we prove that any of these things are true? And we can do it using, various properties of these operations and putting them together in clever ways. But there's actually a much easier way to prove a lot of these things. And this is to use something called a membership table. And so let's try to prove that A union B, A union A intersect B is equal to A. Let's just prove this thing. And we want to prove this without doing too much work. We don't want to think too hard about this. So we've got two sets A and B. Okay, remember from Monday what it means to say that two sets are equal. It means they have exactly the same elements. So if we pick any element in the universe, exactly one of two things should be true. Either, if that element is contained in here, it's also contained in here. Or that element is not contained in here, and it's also not contained in there. If we can show that that's always true, then we can say this is equal to that. So more general, if you want to show two sets X and Y are equal, all we have to do is take every element in the universe and show that either it's contained in both of these or it's contained in neither. That's what it means to say that these two sets contain exactly the same things. So take the number 3. If it's in X, it's got to be in Y. Take the number 5. If it's not in X, it can't be in Y. Well, the universe potentially contains a huge number of things, and we don't want to go through every possible thing in the universe. and show, that it's exactly in both sets or in either set. But we can use a trick. So let's think of some element x. Just imagine some element x. Doesn't have to be a particular element, but it's something from the universe. And let's see what happens depending on whether or not x is a member of A and x is a member of B. So what I'm going to do is, if I pick an element x and it turns out not to be a member of A, I'm going to write a 0 here. And if it turns out not to be a member of B, I'm going to write a 0 here. And I'm going to make a column for A intersect B. And so I'm picking one element. Just think of one element. And I don't know what element I'm thinking of, but I'm supposing that the element I thought of is not in A and it's not in B. So question, is that element in the intersection of A with B?
No.
It's absolutely not. Doesn't matter if it was a 1 or a Q or a smiley face. If it's not in A and it's not in B, it's not in the intersection. Now suppose I think of an element and it's not in A, but it turns out it is in B. Is that element in the intersection?
No.
Right? Because remember, the intersection is a set of things that are in A and in B. So if I pick something that's not in A, it can't be in the intersection. And if I pick an element that's in A but not in B, same thing, it can't be in the intersection. But if I happen to pick an element that's in A and in B, well, by definition, it's in the intersection, because the intersection is a set of things that are in A and in B. So if I thought of an element X that turned out to be in A and also in B, that element's going to be in the intersection. Yeah, indeed. And so
These
every...
look weirdly familiar.
Yeah, right? Any element that I think of is going to correspond to one of these 4 rows. Either it's in neither set, it's in both sets, it's in only B, or it's in only A. And in each of those cases, I've identified whether or not that element is in the intersection. Well, just for completeness, let's look at the union. So if my element's not in A or B, is it in the union?
No.
No, because the union is a set of things that are in A or B. But if it's in B, even though it's not in A, it's going to be in the union, because the union is a set of things in A or in B. And if it's in A, it's certainly in A or B. And if it's in both of these, it's certainly in the union. So that's a membership table for the union.
Literally and or tables.
Literally and or tables. And we don't need this one for this particular proof, but we'll put it down here because it's a good thing to have written down. But now let's look at A union A intersect B. And so we want to look at the union of this column and this column. Well, 0 and 0, if our element's not in here and it's not in here, it can't be in the union. If it's not in here and not in here, it can't be in the union. If it's in A, it certainly is in the union. And if it's in both A and A intersect B, it's in the union. So this is called a membership table. And this is the membership table for, A union A intersect B. And now we just make this observation that this column and this column match exactly. What does that mean? Any element that you think of, anything from the universe, if it's contained in A, it's contained in A union A intersect B. If it's not contained in A, it's not contained in this expression. And if it's not in this expression, it's not in A. And if it is in this expression, it is in A. So any element of the universe belongs to both of these sets in exactly the same cases. It's either in both of these sets or in neither of these sets. That's the definition of saying this is equal to that. So this membership table proves that A is equal to A union A intersect B. And yeah, this is just a good old truth table, right? This is how we proved Boolean identities in 250. We wrote out the truth table, we showed that the two columns were equal in all cases, and then we said, okay, these two expressions are the same. So exactly the same thing works here. All right, you ready to go on? We're moving into weirder territory now. So we can take the union or the intersection of more than two things. We could say something like A union B union C. And we could calculate this by first taking A union B and then unioning that with C. Or we could take B and C and take their union and then union that with A. And these are all the same thing. And that's what we call associativity. So we can move the parentheses around. The order in which we do unions is not important. And that kind of makes sense, right? The union of these says, okay, grab all the things from A, B, and C, throw them all on the table, that's your union. Well, it doesn't matter in what order I grab the things from those sets and put them on the table. I could do A and B first, or I could do B and C first. And so we can do these things in any order we want, and that's useful for the following. If we have a collection of sets, let's call it A1, A2, A3, A4, A5, we can write their union A1 union A2 and so on. We can write a shorthand notation for this, which would be something like the union from I equals 1 to 5 of A subscript I. This is like summation notation that you see in algebra. It's a shorthand. It's a concise way of writing this big long expression by saying, hey, let's just take, A1, A2, A3, A4, A5 and throw a union in between them. Alright, so that's just a notation, and we can do the same thing for the intersection. We can say take the intersection, say from I equals 1 to n of A sub I. That means A1 intersect A2, intersect A3, all the way up to AN. So let's look at a weird example. So I'm going to define a collection of sets, A sub I, where AI is going to be a set of integers containing I plus 1, I plus 2, and so on. Where I is 1, 2, 3, etc. So for example, A1 is the set 1, 2, 3, 4, 5, and so on. A2 is the set 2, 3, 4, 5, and so on. A100 is the set 100, 101, 102, and so on. Right? Everybody clear on what A sub I means? It's just the set of integers starting from I. So let's play with these set operations. So I'll keep this up here for a minute. So if I want to union the first n of these sets, what do you think I end up with? And this is a case where working with some specific examples might lead us to insights.
Is that A1 times 2 up the bottom in there?
This one,
Yeah.
that's A100.
Oh, okay.
So what if I union the first n of these sets? This is normally a problem I'd have people standing in front of a board in groups working on. Not going to happen this year, but
Thankfully.
yeah. Well, no, it's a good exercise to work on, and it's fun to work on it in groups.
Yeah, I don't like standing in front of people.
Oh, well,
Love it.
then actually it would be a really good exercise because it's a pretty low pressure way to push back on the edges a little bit. At least in the past, I've had students who hated this part of the course, and by the end of the course, they were just like totally into it. But anyway, we're a friendly group, and we're remote, and we get to work in groups of one. So, but yeah, so let me add A3 on here. So that's the integers from 3, 4, 5, 6, and on up. And suppose I take the union from 1 to 3. So I take A1 union A2 union A3. What do I end up with?
All of the numbers.
What's
all numbers from 1 to infinity.
Yeah, so what's the name of that set?
All real, the real numbers. What?
No, you're right there. So what's A1 union A2? Here's A1, here's A2.
Is it not real numbers? I forget which one.
1, 2, 3, 4, 5.
Yeah, it's 1, 2, 3, 4, 5, and so on, which is just A1. If I take A1 union A2 union A3, what am I going to get?
1, 2, 3, 4, 5.
1, 2, 3, 4, 5, exactly, which is just A1. And if I were to do A1 union A2 union A3 union A4 union a bunch of other things, I'm still going to end up with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. This is always A1. That's just, the way I define these sets. That's just something that happens. There's no deeper reason why this is true. It's just kind of what happens. Now, what about intersections?
Ooh.
So same thing. Let's work with some examples. Let's look at the intersection of A1 with A2. So what's the stuff in common between A1 and A2?
2 and onward.
Cool. 2, 3, 4, 5. Which is good old A2. What about A1 intersect A2 intersect A3?
3 and onward.
Which is A3. So if we try to generalize this, we can imagine that if we took A1 intersect A2 intersect A3 all the way up to intersecting AN, we might reasonably believe we would get AN. And that turns out to be correct. And once you've done some examples and you've postulated that this is the case, you can sort of go back and think, why would this be true? Well, A1 is the biggest of all of these sets in the sense that all of these other sets are subsets of A1. And so I'm starting with A1 and I'm just throwing in things that are already in A1. Right? A7 is, the stuff starting from 7 on out. Well, that stuff is already in A1. So when I throw all of those together and I get rid of the duplicates, I'm just going to end up with A1. But with intersections, I'm looking for the things that are in all of these sets. Well, A1, has all my numbers starting from 1. A2 has all my numbers, but only starting from 2. It's missing 1. And A3 is missing 1 and 2. And A5 is missing 1, 2, 3, and 4. So if I intersect up to AN, I know that my last set's going to be missing 1, 2, 3, 4, 5, all the way up to n minus 1. But it's going to have everything from n on out, so I'm going to get AN.
It weirdly feels like I'm in calculus and I'm thinking about, like, the point system on tangent lines and that kind of thing.
You are. This is all related. And there's a subject of mathematics called real analysis, and real analysis is like a more abstract version of calculus. And this is a beginning point for real analysis. So yeah, this is all gloriously related. All right, let's make it really weird now. Let's imagine the union from I equals 1 to infinity of AI. Now there is no A subscript infinity, but this means I want to do A1 union A2 union A3 and keep going and going and going and take the union of this infinite number of sets.
Wouldn't this just be A2 lower infinity? Or just just A
Everything?
It turns out to be everything. It's exactly the same as in this case. I just get A1. Because all of these other things that I add in to my union contain stuff that's already in A1 and nothing extra. So that just ends up being A1.
Does this mean that the intersection of infinity?
So what does this mean? What do we get when we intersect all of these?
Is it nothing?
Is it?
I mean, if it intersects everything with everything, you're gonna come out to nothing, right?
So yeah, the naive approach would be to say, well, this should be A infinity, but there is no A infinity, right? For a finite set, we ended up with AN. And this is an infinite set. This has an infinite amount of stuff in it. A1 million still has an infinite number of things in it. It goes from 1 million to 1,000,001, 1,000,002, on and on and on up. There's still an infinite number of things. But when we take the intersection of all of those, yeah, we end up with exactly the empty set. And that should be fairly alarming, depending on your mood. Because each of these is an infinite set, and each of these has an infinite number of things in common with every other set in this list. But yet when we take the intersection of all of them together, we end up with big fat nothing.
This feels like a weird wormhole.
Yeah, yeah. And we can convince ourselves that this is reasonable if we think about the other possibility. Suppose that this is not the empty set. Suppose that this big long intersection contained the number 17. Well, I can prove that's not possible. Because A18 does not contain 17, and since I'm taking the union with A18, 17 can't be in that union. Okay, well maybe, the number 2 million is in this union. Well, if I look at A 2,000,001, it doesn't contain this number. And so when I get to where I take the union with A 2,000,001, this number will not be contained in the intersection. And any number you think of, you can do the same argument and show that it cannot be in the intersection. Your only conclusion is there's nothing in the intersection. It's got to be the empty set.
This is like similar to like dividing with like using limits to infinity and dividing over infinitely growing.
Yes, definitely. And when you study limits in calculus, the whole idea is that, as you approach some point, something is happening, but that may be very different from when you get to that point, right? 1 over x gets smaller and smaller as x gets bigger. 1 over x gets larger and larger as x gets closer to 0. But when x actually reaches 0, something very different happens. 1 over x becomes undefined. And you can define limits in terms of this kind of mechanics. All right, question in chat. Does the existence of real analysis support the existence of fake analysis? It does not. It supports the existence of complex analysis, where we do all of this stuff over complex numbers instead of real numbers. And you can develop calculus over complex numbers instead of reals, and that's something called complex analysis. And that's a beautiful subject of mathematics that has so many applications and so many surprises. All right, so let's take a 5-minute break, and then we'll come back and we're going to talk about some weirder stuff. So let's take a break and let's come back in, let's see, it's 4:11. Let's come back in like 4.5 minutes, or 4 minutes. All right, let's talk about paradoxes. So paradox is a thing that doesn't make any sense. It's something weird. You can find paradoxes in science fiction books and Star Trek episodes, and occasionally in life. Paradoxical, right? Sort of nonsensical, something that cannot be, yet it is. So I want to look at a specific paradox from set theory. And this is something called Russell's paradox. And so Russell was a mathematician who systematized a lot of mathematics. He was also a philosopher and a writer. And, you know, when we started talking about sets on Monday, we talked about a set is a collection of things. And I mentioned that, you know, naive set theory is where you just sort of have this kind of intuitive notion of what a set is. And that if we're not careful, we can get into trouble. So we're going to get into some trouble here. We're going to create a paradox in set theory. And so let's make a definition. We can define whatever we want, right? We can define two sets to be disjoint if their intersection is empty. We can define a set to be finite if it contains only a finite number of things. So I'm going to make a new definition, and the definition may sound really strange, but it's just a definition, right? I can define somebody to be purple if their first name has an odd number of letters in it. It's just a definition, right? So I'm going to make a definition for sets. So a set S is called self-consuming if S is a member of itself. Well, what does it mean for a set to contain itself? It's kind of a silly notion, right? So suppose S is this set containing, you know, 3 Sharpies. Well, this is not a self-consuming set because it contains, you know, 3 writing instruments. It does not contain a set. It doesn't contain the set of reals or the set of integers or a set containing 3 Sharpies. So this is not a self-consuming set. And in fact, most sets that we can think of are not self-consuming. So for example, the set 1, 2, 3 is not self-consuming because it doesn't contain the set 1, 2, 3. And you know, sets can contain sets, so I could make a set containing a 1, a 2, a 3, and the set 1, 2, 3. Well, this is a set containing 4 things now. An integer, a bigger integer, and a set. But this set is still not self-consuming. To be self-consuming, it would also have to contain this set itself. Alright, so most sets that we can think of are not self-consuming. But if there was a set that contained itself, we would say it's self-consuming. Alright, so that's just a definition. But it's a suspicious sounding definition.
Is this like an I thing? Like, it doesn't exist?
Yeah.
Like the square root of negative 1, kind of?
Kind of, yeah. And it's hard to imagine a self-consuming set. But, you know, if a set happens to have this property, we'll say it's self-consuming. Alright, so I'm going to use this property to define another set. Let B equal the collection of all sets that are not self-consuming. So B certainly has a lot of things in it. B would have to include, you know, this collection of 3 Sharpies. It would have to include this set. It would include this set. It would include the integers and the reals and the odd numbers and the set of all emojis that are available on Android but not iPhone, and so on and so forth. Any set that doesn't contain itself belongs to B. So it's probably the set of all sets. So here's our question. Is B self-consuming? So does this set B contain itself?
No, because if it did, then
That hurts my brain because I would say yes, because if B is the sum of all sets, then we would have to include B within that set, wouldn't we?
So if B is a set of all sets that are not self-consuming, and B is not self-consuming, then B should be included in here. But if B is included in B, then B is self-consuming. So the answer must be yes, B is self-consuming. But if it is, then B should not be included in this, because this is only the sets that are not self-consuming. So B does not contain B, which means B is not self-consuming.
This hurts.
Good. You got it then.
paradox.
Paradox. So, we think of a question like this as having a yes or no answer. But we've set things up so that if the answer is no, we can prove the answer is yes. And if the answer is yes, we can prove the answer is no. So the answer can't be yes or no, but it's got to be one of those. That's a paradox. And it's the classic feel of a paradox. So Star Trek, there's an episode where they're trying to overpower these androids, and so Kirk tells one of the androids, everything I say is a lie, and then he makes a statement, I am lying right now. And the poor android's like, well, everything you say is a lie, so if you tell me you're lying, you must be telling the truth, but you can't be telling the truth because everything you say is a lie, so you must have been telling the truth when you said you were lying, and the android melts down, and they manage to regain control of the Enterprise. Same idea, right? You're basically setting things up in a way, and then you make one little twist, and everything sort of crumbles apart.
You
And
know
this-
what? This kind of feels like a never-ending while loop.
Yeah. Very much, very much. And this is related to kind of where my life went in the mid-'80s. I took a detour that I'm still on, many years later, into a research area that I'm still continuing to work in today. And it stemmed in part from analysis of this kind of thing. This putting things in one direction and then all of a sudden realizing, like, with a little twist, suddenly you can turn it back on itself. So paradoxes are interesting, and this was kind of a big problem in mathematics around the turn of the 20th century, 1900s, because, set theory is pretty straightforward business in a lot of ways, and all of a sudden you've got a pretty simple, fits on half a page description of a question that cannot be answered. Not just that we can't find the answer, but that any answer leads to a contradiction. And so that's a little disturbing to mathematics types. And so Whitehead and Russell, Whitehead is another mathematician philosopher, Whitehead and Russell set about trying to sort of clean things up, and trying to do a more careful definition of mathematics. So instead of making a set an arbitrary collection of things, you can start putting a little more specific language on that and saying, well, what kinds of things can we have in a set? And if you're careful, you can avoid being allowed to make statements like this, the set of all things that are not self-consuming, and you can get yourself out of some of these paradoxes. So in the early part of the 1900s, Whitehead and Russell set about trying to do this with mathematics. And they produced a 2-volume set called Principia Mathematica. And the whole book looks like this. It's just page after page of stuff. These are all statements and proofs of statements. And they basically needed to redevelop arithmetic and mathematics from the ground up and try to do it in a very sort of rigorous way to try to come up with a system of arithmetic and mathematics that was free of paradoxes. And this is one volume. It's 719 pages, and then the other volume is about the same size. This is volume 1. So this is, thousands of pages of mathematical description and proof.
I've heard of dry reading, but that's ridiculous.
I don't know who proofreads this. I mean, I've written papers significantly smaller than this that, as far as I know, nobody has ever read completely, including myself. But this was a labor of love, and it's incredibly intricate.
Without reading it.
If you write it with somebody else, sometimes you put it together, but you haven't actually read the whole paper. And it's like, hey, can you look over my stuff? Sure, but you actually don't. So yeah, somebody said in chat, 83 pages to prove 1 + 1 = 2. It's actually worse than that. So down here on page 379, we're proving more propositions, more theorems. And here's, 54.43, and at the end of this, there's a note that says, from this proposition, it will follow, when addition has been defined, that 1 + 1 = 2. So 379 pages to put together some of the machinery that eventually gets used to show that 1 + 1 = 2. So this is otherworldly stuff. And it's a fantastic achievement. I think it's one of the highlights of human creativity. And it turned out to be somewhat in vain, because later in the 1930s, a relatively unknown mathematician named Kurt Gödel came along and basically threw a monkey wrench into all of this. And what Gödel showed was that basically, if you develop a system of mathematics, you may find that it has paradoxes, contradictions, things that, can't be either true or false, or maybe things that are both true and false. And if you start removing things from what you're allowed to do to try to get rid of those contradictions, you'll end up with things that you cannot prove or disprove. You'll end up with incompleteness. And if you add enough assumptions, enough axioms to resolve all of those incompletenesses, you end up introducing paradoxes. And what Gödel showed was there's no sweet spot in between those two extremes. Either you've got too much stuff and you have contradictions, or you have not enough stuff and you have an incomplete system. And there's no sweet spot in between. And it's not that we're not clever enough to come up with this, it's a fundamental property of arithmetic systems that you always have one or the other, but there's never a golden balance point where you have a perfectly complete, paradox-free system of arithmetic.
Veritasium did a video on the incompletes of math. It's really good.
Cool. Who's that?
Veritasium. He does a lot of physics and math
Okay.
videos on YouTube.
Cool. Yeah, so if you're interested in this, you can start with Kurt Gödel. And the wiki page will lead you on a long, glorious journey down a big rabbit hole. YouTube channels like Numberphile is another good one. There's lots of videos out there that talk about this in different ways. Numberphile has a bunch of good stuff related to stuff we're going to do in this course. But this is a fascinating result from the 20th century, and has a number of interesting implications, possible tie-ins to things like Heisenberg's uncertainty principle and all kinds of things like that. And you can buy, books that go through Gödel's proof. In fact, I thought I had one here. Here's one treatment. This is actually a 2-volume set. So this is on formally undecidable propositions of Principia Mathematica and related systems. And it's not that long a proof. It's pretty intense to try to understand it, but it's doable. It's on my list. Okay, cool. Someone posted a link in chat. All right, so we have incompleteness. We have paradoxes or things we can't prove, and that's okay. This is not going to affect us in this course, right? The set theory we're going to stay away from those edges. But I think it's worth noting that, you know, such things do exist, and being aware of that. And as computer scientists, you know, we can pretty much write programs to do anything we want our programs to do, but there are programs we cannot write. And we'll touch on these throughout the course, and we'll definitely talk about them the last day of the course when we talk about the halting problem. But there are programs that you cannot write, and it's not just because you're not smart enough to write the program, it's because it's fundamentally impossible to write these programs.
Either that or it may break the computer.
Or it may break the computer. So yeah, so this gets fairly thought-provoking. But let's continue in this vein for a little bit, and let's go to story time. So if you've got some like hot chocolate or cookies, this is a good time to have those. And let me share a story with you. And this story is fictitious. It's based on a real person, but it's a made-up story for the sake of exploring something. So we're going to explore sizes of infinity. And infinity means, you know, a really big bunch of stuff, a large number of things. And we know that, you know, there's an infinite number of integers, and there's an infinite number of even numbers, and there's an infinite number of fractions, and there's an infinite number of reals, and all of this. But let's explore the sizes of these infinities. Cool. All right, and so we're going to talk about something called Hilbert's Grand Hotel. So David Hilbert is a real mathematician. He was instrumental in developing mathematics through the 1800s and the early 1900s. He posed a set of questions at a congress in 1900 that he suggested mathematicians work on for the next century. So these are called Hilbert's problems. And they helped guide the development of mathematics over the next 100 years plus. Some of these questions were answered, some of them remain unanswered, some of them turned out to be unanswerable. So Hilbert was a mathematician, professor, teacher. That part's true. So here comes the fictitious part of the story. So the story goes that, you know, David Hilbert got tired of mathematics. He'd been teaching for a long time. He got tired of, you know, going to committee meetings and stuff, and so he decided to retire. And he was famous, he had some money, so he moved to a little town in Switzerland and had a cottage and would go out fishing in the morning and make pancakes for breakfast. And that was great for a year or two, but he started to get bored, you know, because he was a genius of mathematics and he was always doing things, and fishing and eating pancakes, well, it was good for a while, but now he's bored. So he decides, okay, I need a new job. So I don't want to go back to mathematics. But he notices there's an hotel across the street that's closed. It's out of business. And he thinks, you know, I bet I could run that hotel. So he goes over, he buys the hotel, he puts a sign on top, Hilbert's Hotel. He fixes it up a little, and he advertises, you know, come stay at Hilbert's Hotel, cheap rooms, you know. And guess what? It's a huge success, you know, because everybody knows David Hilbert. He had students, he had colleagues, and people start to hear, hey, David Hilbert has a hotel in Switzerland. Let's go stay there for the weekend, you know. So he opens the hotel, and pretty quickly he's like selling out every night. All the rooms are full. And he starts making some money. He's like, hey, this is easier than being a professor. If I had a bigger hotel, I could make more money. So he takes some of the profit that he's made and he adds a new wing to the hotel. And now the hotel is twice as big. And, people are going there and having a great time and telling their friends. And so every night the hotel is sold out. And so after a little while, he takes the new profit that he's gotten from that and he makes a new wing. And now his hotel is bigger. And he keeps doing this. And no matter how big he makes the hotel, everybody wants to come and stay there. And so the hotel is filled up. He makes lots of money. He saves the money. He invests and builds more rooms on the hotel. And eventually, through some loosely defined miracle, he ends up expanding his hotel so large that it has an infinite number of rooms. And so now this is called Hilbert's Grand Hotel. Okay, so what do we mean by an infinite number of rooms? So if you look at the hallway of Hilbert's Hotel, there's a bunch of doors. And each door has a room number on it. 1, 2, 3, 4, 5, and so on. Every door has a number on it which is a positive integer. And when I say there's an infinite number of rooms, it does not mean there's a door with an infinity symbol on it, because infinity is not an integer. But what I mean is, if you think of any positive integer, there is a room with that number on the door, and there's another door to the right of that with a bigger number. In fact, there's a never-ending set of doors to the right of that with bigger numbers. Okay, that's what we mean by an infinite number of rooms. So that's really important. There's no room with an infinity on the door, but any number you can think of, 10,219,073, I can find a door with that number, and there's a bunch of doors with bigger numbers. All right, everybody got the setup? So people are coming to the hotel and they're staying and this is all great. And it's coming up on Hilbert's birthday. And yeah, definitely. Someone said, I think I've seen this in a horror film. So it's coming up on Hilbert's birthday. And he decides he's going to throw a birthday party for himself. And people are like, yeah, that's a great idea. And people start talking, from university to university. And people are excited. They want to come and stay at Hilbert's Hotel for his birthday, there's only a finite number of people on Earth. So, you can easily fit all those people in the hotel. But it turns out that in Zurich, there's a lab of physicists, and they're working on parallel universe theories. And at the moment that they get the invitation to this party and they open it up and the physicist reads it out loud, he happened to have a portal open to an infinite number of parallel worlds. And so now this infinite collection of worlds is filled with physicists who have heard about this party at Hilbert's Grand Hotel. And word gets out through these other universes, and the ones that have the ability to travel to this universe decide, hey, we're going to go to Hilbert's birthday party, right? So it turns out that an infinite number of people show up for this party. All right, so let's number these people. Let's think of these people as just, let's call them the guests. And this is the rooms. And let's number our guests 1, 2, 3, 4, 5, and so on. Okay, what do I mean by an infinite number of guests? There's no guest whose number is infinity. What I mean is, if you think of any positive integer, there's a guest with that number, and there's other guests with higher numbers. All right, so these guests show up in town, and they go to Hilbert's Hotel, and they ask for a room, and the clerk, who's very skilled at their job, hands out keys, and comes up with an easy assignment system, which is guest 1 will stay in room 1, guest 2 will stay in room 2, guest 3 will stay in room 3. Now, even though there's an infinite number of guests, because there's an infinite number of rooms, everybody gets a room. Right? And guest number, 17 trillion ends up in room 17 trillion. So everybody's in a room, and every room is filled. If you pick any room, look at the number on the door, the guest with that number is sitting in that room. So the hotel is perfectly filled. All right, so here's our setup now. We've got an infinite number of guests, infinite number of rooms. Every guest has a room, every room has a guest. It's like a one-to-one correspondence. And everybody's happy. Everybody can unpack their suitcase, take a shower, and then they can go to the party, they can eat food, they can dance, and so on and so forth. So this is all great, except for the one graduate student whose car broke down outside town. And as the student was driving to the hotel, their car sputtered and it backfired and the engine died. And they were near a garage, so they walked to the garage and said, you know, hey, my car is broken down, can you help me? The mechanic came out, towed the car, did some work, replaced a gasket, got them going again. But it took a few hours. So this student comes driving into town about 10 o'clock at night. Really wants to go to this party because he was one of David Hilbert's students. And he goes up to the desk clerk and he says, you know, I'm hoping you can find me a room in the hotel. And the clerk says, sure, no problem, give me a minute. And he goes in the back room, does some things, come back, hands the person a key and says, here you go, enjoy your stay. So here's the first question of the story. Given that this infinite number of rooms was completely filled, how did the desk clerk find a room for this new guest? And we don't want to kick anybody out, and we don't want to double anybody up in a room, by the way.
I read the story. Can I say the answer or stop?
If you already know the answer, let's wait a minute and see if somebody else...
I would say find a room that hasn't been taken.
Except every room already has somebody in it. Right? Remember, the hotel is completely filled. So if every room is filled, how can you find an empty room for this new guest? You could build a new wing, but let's not do that because it's 10 o'clock at night.
Weirdly, it doesn't make sense to me because even though there's an infinite number of people, adding one person to an infinite number of people would still just mean it's an infinite number. So the amount of rooms would still be infinite and would be able to include one person.
Right. So how do you do that? Well, someone just said it in chat, right? Take the person who's in room 1, ask them to move to room 2. Ask the person who's in room 2 to move to room 3, 3 to 4, and so on. Everybody moves down one room, which only takes a few minutes, and now room 1 is free. That's where the new guest can stay. And that works perfectly well. Nobody has to double up. Nobody gets kicked out. Because there is no last room. There's no room at the end that the person's not going to have a room to move into. Because for every door, there's another door to the right. So this is guaranteed to work. So push a button under the desk that lights up a sign in each room and says, you know, sorry for the inconvenience, please move one door to the right. And each person gets up and moves over one room, and now room 1 is free, that's where the new guest stays. So here's the first weird thing about that. Infinite number of rooms, infinite number of guests. One-to-one correspondence. Each guest is in a room, each room has a guest. If I add one more thing to this set, there's still a perfect one-to-one correspondence between the rooms and the guests. And so this is what you just said a minute ago, adding 1 to an infinity doesn't really change the infinity. Well, that's exactly what's going on here. We can add one more thing to this set of guests and still have a one-to-one mapping between the set of rooms and the set of guests. I don't know if it's related to Banach-Tarski.
I don't think it is.
All right. Well, this is great, right? Our late graduate student with the broken down car can still find a room. They can unpack, take a shower, go to the party. Now, clearly, if another guest shows up late, they can do the same thing. Everybody can move down one room. New guest can go into room 1. We can do that, 2 times, 10 times, 100 times. Not a problem. All right. Well, remember the physicists and the parallel universes and so on and so forth. And it turned out there was a parallel universe with another Hilbert's Grand Hotel. And a bunch of people mistakenly thought that's where the party was. And so in a parallel universe, there's an infinite number of rooms, an infinite number of guests, but it's not the right party. Somehow they know which one is the real David Hilbert, right? And so they figure this out and they say, hey, we should have gone to these coordinates instead, So this infinite number of guests teleports into our universe, teleports to the hotel, walks up to the clerk and says, hey, there's an infinite number of us here. Can you find rooms for us? And again, the clerk says, sure, no problem, give me a minute. He does some stuff, and he hands out a set of keys and says, here you go, enjoy your stay. So here's the next question of the story. If you have an infinite number of new guests and this completely full hotel, how can you fit that infinite number of new guests into the hotel without doubling up, without kicking anybody out?
I don't know the answer to this one, but I'm going to make a guess.
Okay.
You'd match... Well, no, that already fell flat.
Okay. So we can add 1 guest, 2 guests, 10 guests, 100 guests, but how can we add an infinite number of guests? And an infinite number, we can't just add them one at a time because we'll never finish. Go ahead.
Again, it doesn't matter
Why is that?
because they're both infinite. Infinite is infinite.
Infinite is infinite.
Well, there's no empty room at the end for them to go into, basically, is what he's saying.
I know there's just an infinite amount of rooms.
There are, and we can take advantage of that. We can actually come up with an approach to fit these people in, and it's not too much work. So the clerk
Would you
lights
have
up another
every
sign.
physicist
Go ahead.
Go across? Would you have every physicist go across with the same number matching for each room or something? And then they'd each shuffle down 2 or something? Or
Something like that. So the clerk lights up another sign in each room which says, sorry for the inconvenience. Please, if you are in room N, move to room 2 times N. And so the person in room 1 moves to room 2. The person in room 2 moves to room 4. The person in room 3 moves to room 6, and so on. Nobody can't find a room, right? Whatever your guest number is, there's always a room number with twice that number. But after you've done this, guess what? All these odd-numbered rooms are free. And there's an infinite number of them. And now you take your new guests and you can number them, 1, 2, 3, 4, 5, and you move each guest to, room 1, 3, 5, 7, 9. And so now you've doubled, in some sense, the number of things in this set of guests, but you still have a one-to-one correspondence to the number of rooms.
Really hoping that the customers can do math.
Definitely. And nobody has to walk an infinite distance. Now, the person in room 1 million has to get to room 2 million. That's going to take a long time. But it's a finite amount of time. It's 1,000,000 steps, right? So it's not like anybody's going to have to walk forever to get to their room. But it might be a really long walk. But you can still do this. All right, so this is looking like a pretty grand hotel, right? It can handle overflows of guests. No problem. But now something unfortunate happens. There's another hotel across town called Blauman's Grand Hotel. And Dr. Blauman has a hotel with a series of doors. And the numbers on the doors are all real numbers between 1 and 2. So this is room 1.0, this is 1.1, this is the square root of 2, this is, 1.5, this is 1.0001, and so on. Every number between 1 and 2, you can find a door with that number on it. And there happened to be a party going on this side of town, and a lot of guests, wanted to go to Blauman's Grand Hotel. And so we can number our guests and imagine our guests are numbered accordingly. And each guest is in a room, and each room corresponds to a guest. And this is a really, really big hotel, right? Infinite number of rooms, infinite number of guests. Well, this party's going on, but eventually, the music from this party is so fabulous that it reaches the other side of town, and people at this hotel realize, we should be at Hilbert's hotel. That's where the real party's happening. And so all of these guests get up and they walk across town, and they come to Hilbert's hotel, and they walk up to the clerk and they say, we would like rooms in your hotel. Can you help us? And the clerk shakes his head and said, sorry, there's not enough room in the hotel for all of you. And so this is an infinite number of guests. It's, all of these guests that we originally had, and all of these guests with numbers between 1 and 2. But it turns out that's too many guests to fit into this infinite number of rooms. It's a fundamentally bigger version of infinity. And so this cardinality symbol that we have, if we say how big is the set of integers, we can say that's equal to the set of integers unioned, a new guest. So take the set of integers, add one more thing. It's got the same amount of stuff as the original set of integers. And it's the same as the cardinality of the set of evens. But it turns out it's smaller than the cardinality of the set of reals. Even just the reals between 1 and 2. And so there are different sizes of infinity. There's the infinity of the integers, and there's the infinity of the reals. And the reals are somehow a bigger infinity. And we can prove that. So when we look at this cardinality for a finite set, it's just the number of things in the set. When we look at this for an infinite set, it's somehow a measure of how big of an infinity this thing is. But the key to understanding these sizes of infinities is to think about this one-to-one correspondence. If I have two sets that I can put the elements into a one-to-one correspondence, they have the same cardinality. That's what we mean by saying two infinities are the same. So here I had a set of integers, here I had a set of integers plus one extra thing, but I can still find a one-to-one correspondence. And finding a one-to-one correspondence is basically, finding a room for each guest and finding a guest for each room. So these earlier incidents where one guest showed up, two guests showed up, an infinite number of guests showed up, we maintain this one-to-one correspondence. And so we can say the cardinality of z is the same as the cardinality of z plus one more thing. It's the same as the cardinality of if we took two things that were both, the size of the integers and put them together. But now when we have real numbers, we can't find a one-to-one correspondence. And we can prove this. And this is a beautiful little proof. This is not on the exams, by the way. This is just to convince you that this is a fun, interesting subject and course. And it's Wednesday, which is our Fridays. So So let's prove that there's more reals than there are integers. Well, let's first of all prove that we've already seen that if we take something the size of the integers and we add one thing to it, we still end up with the integers. And if we add two things, we end up with the same size of the integers. And if we add twice as many things, we still get the size of the integers. It turns out, if we look at the number of fractions, it's the same as the number of integers. And we can see that by writing down our fractions like this. So let's just, put all of our integers on our two axes, and let's write our fractions like this. I'm not going to do the whole thing. But clearly, any fraction you can think of integers, p over q, is somewhere in this table. It's probably in here more than once. Because, 3 over 3 is the same as 2 over 2. So this collection of numbers is, actually bigger than the number of fractions. But I can find a one-to-one map between this set of fractions and the set of integers. And it's really easy to do. Start up here, move over one spot, come down one spot, move down one, go up the diagonal, move over, go down the diagonal, move over, go up the diagonal, move over, go down the diagonal. I can define a path through this set of fractions, and every fraction is somewhere on this path. So I'm going to associate with each fraction its position along this path. This will correspond to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and so on. It's a one-to-one correspondence. So even the fractions, which are, pairs of integers, has the same size as the integers themselves. But not so with the real numbers. So let's prove that there's more real numbers than there are integers. And let's just pick the real numbers between 0 and 1. Right? That's a tiny collection of real numbers compared to all the real numbers, but we can show that there's more stuff in here than there are integers. And we're going to do this by using what's called a proof by contradiction. We're trying to prove that this is true. We're going to assume that this is not true, and we're going to find a contradiction. So suppose the cardinality of the reals is the same as the cardinality of the integers. That means there's a one-to-one correspondence between these numbers and those numbers. So let me start writing down some of the numbers in here. Let me write down the integers. We're just working with positive integers here. And if you tell me, hey, these things have the same size, I found a one-to-one correspondence between real numbers and integers. Here's what we're going to do. I'm going to say, okay, what number corresponds to 1? And you'll say, oh, that's the number 0.5. And I'll say, okay, what number corresponds to 2? And you'll say, oh, that's the number 0.142857. 142857. What number corresponds to 3? Oh, that's the number 0.9999000. And so you're going to tell me what the correspondence is to each integer. So 4 corresponds to, I don't know, maybe 0.1. And so on. All right, I'm going to use that information you gave me to create a new number. And here's what my number is going to look like. It's going to start with 0 point. The first digit is going to be this digit plus 1. I'm going to take the 5, I'm going to add 1, and I'm going to get a 6. The second digit will be the second digit of the number corresponding to 2 plus 1. So this will be a 5. The third digit will be the third digit of the number corresponding to 3 plus 1. 9 plus 0, well, that's just going to wrap around to 0. 9 plus 1. The fourth digit will be the fourth digit of the number corresponding to 4 plus 1. And so on. Alright, so I'm going to write down a real number between 0 and 1. And I can guarantee you that number is not found anywhere in this map that you gave me. It can't be. This number cannot be the first number because it differs in the first digit. This number cannot match the second number because it differs in the second digit. It can't match the third number because it differs in the third digit. It can't match the 100th number because it will differ in its 100th digit. And if this is truly a one-to-one correspondence, there's some integer n that should represent this number. But it can't because that number and this number will differ in the nth digit. And so that's enough to prove that, there is no one-to-one mapping. And so the set of reals is fundamentally bigger than the set of integers. Thank you. And that's a proof technique called diagonalization. And it comes from moving along the diagonal here and sort of, making that little twist. And it's a diagonalization argument that Gödel used in proving his incompleteness theorem. Thank you. So it's a really cool proof technique. All right, so you ready for the weird part now? So we got 7 minutes left. So let's talk about something called the continuum hypothesis. And this is where I'll leave you for the week. So we know that cardinality of the integers is the same as the cardinality union, some singleton set. And we also know that this is the same as the cardinality of the rational numbers, the fractions. Right, that's something we got by going down that diagonal. But we've just seen that the integers has a smaller cardinality than the set of reals. There's more stuff here than there. So the cardinality of this is something called Aleph 0. So whoever asked about Aleph a while ago, yes, these are Aleph numbers. And we know the reals have a bigger cardinality than the integers. So here's the question. Is there some other set, let's call it S, that's bigger than the integers but smaller than the reals? In other words, is it possible to add stuff to the integers so that we get something that's got a fundamentally bigger size of infinity but still not as big as the reals? In other words, is there something bigger than the integers, smaller than the reals, something in between these two infinities? That question is called the continuum hypothesis. It's sometimes just called CH. And the continuum hypothesis claims that there is no such set. That as soon as you find a set bigger than the integers, you're at something the size of the reals. The first set that's bigger than the integers, that has size what we call Aleph 1. And so the continuum hypothesis basically says, is the cardinality of the reals equal to Aleph 1? Or is it bigger than Aleph 1? Is there some set smaller? And so people have studied this. and tried to figure out, is there a set bigger than the integers, smaller than the reals? So we've only got about 4 minutes left, so let's just do a thumbs up. If you think the continuum hypothesis is true, in other words, there is no set between Z and R, give me a thumbs up in chat. We'll do math by democracy here. Got one thumbs up. Or if you don't know how to do a thumbs up, just say true in chat. Or thumbs up. Cool. More thumbs, good. Popping in. If we get more than 8 votes, democracy rules and CH is true. Alright, how many people think that the continuum hypothesis is false? And that in fact there is some set between Z and R?
Whoops, I meant to vote for this one.
So this has not been proven to be true or false. But here's the funny thing about it. What has been proven is that you cannot prove that CH is true, but you also cannot prove that it's false. There's no proof that this theorem is true or that it's false. That's why it's called a hypothesis. Right? It's another paradox in some sense, or an incompleteness. There's not enough stuff in our mathematics to prove this one way or another. Now what that means is we can never discover a set between Z and R, because if we did, we'd know CH was false. But we cannot prove that there is no such set, because if we did, we'd know CH was true. So this is a weird class of problems called formally undecidable. And there's a whole branch of logic which studies formally undecidable propositions. And this relatively simple statement, it took us, a half hour to get here, but this relatively simple statement cannot be shown to be true or false. And again, it's not because we're not smart enough at writing proofs. It fundamentally is neither true nor false. It's a statement
We
whose...
just haven't figured it out yet.
It's worse than that, though. It's a statement whose truth value lies outside of what is demonstrable with our mathematics. It's fundamentally undecidable. It's not possible that, a million years from now, when we have giant heads inside fish tanks, that we come up with a proof for this or a disproof for it. It's fundamentally undecidable. And that's been proven. And that's similar to Gödel's proof, and it's similar to the diagonalization. So yeah, if we could invent math too, then maybe we could find a way to do this. All right, so that was pretty weird, but it's stuff I like to talk about at the beginning of the course, just to kind of reinforce this notion that something like a set, or putting two sets in correspondence to one another, might seem like a really bland, simple thing to do that's easy to understand, but it can get us into all kinds of weird places in terms of logic and meaning. And a lot of what we do in this course, we're not going to usually get into stuff this weird, but a lot of what we're going to do in this course, like when we talk about counting, we'll start off, with 1, 2, 3, 4, 5. We'll end up with, some really unexpected things that we can show, or problems that we can solve. And so that's just some of where some of the stuff can take you. All right, so Monday we will come back to Earth a little bit and talk about functions, and I'll describe functions in terms of set theory. And then we'll do a few mechanical things. We'll talk about summations and sequences and a little bit about matrices, and that will pretty much do us for set theory. And then we're going to start talking about proofs. And we'll get into proofs on Monday. We'll do more proofs on Wednesday. and we'll talk about the next homework assignment. We're going to miss the 17th and also a day in February. We have 2 Monday holidays this quarter, which unfortunately is 4 hours of lectures, so we might make some adjustments to the homework schedule accordingly. But for now, we'll plan to finish up sets on Wednesday, start talking about on Monday, start talking about sets, logic, and then build up from that next Wednesday. All right, cool. Have a great afternoon. Pop by office hours if you got questions on the homework, and I will see you next time.
Take care, Nick.
Take it easy.
Thank you.